In last video, we defined conditional expectation. In practice, we often treat conditional mean, conditional expectation, as a random variable. In a lot of cases, we do this, and this can appear confusing to some first-time users of conditional mean. Let me explain in this video how we can treat conditional mean as a random variable and what kind of random variable it is. To explain how we treat conditional mean as a random variable, let's first define a function. We can all agree that expected value of y given x equals a realization little x is a function of x. Why? Because it gives you a value for each value of little x. That is a function of little x, and we can call that function g of little x. G is just a name we give for this function, a shorthand for this function. Now realize g is a function. Therefore, g of x, if we plug in the random variable x into g, that becomes a function of a random variable. Previously, we have discussed a function of a random variable becomes a new random variable. So g of the random variable x is a random variable. Now we have this realization. We can define the notation e of y given big X without the equal some realization here. E of y given the capital X. We can define this notation we haven't used before. We can define this notation to be that function g of x we just introduced. So this notation is the function g evaluated at the random variable. It's the function of the random variable x. And that function is defined here. You see, since g of x is a function of a random variable, and therefore it is a random variable, this ey given x, this new notation we just defined, is a random variable. And this is the sense in which we treat conditional expectation as a random variable. It is a function of the conditioning variable x. Similarly, the conditional variance given x is also a random variable. And it's also a function of x. Now, since expectation of y given x, this notation denotes a random variable. It's a function of big X. We can define traits for it, or we can figure out the traits for this random variable. What is the expectation of this random variable? Expectation of this random variable can be calculated using the definition of expectation. It is a weighted average of all the possible values, which are denoted by ey given x equals some given little x. And we average over little x with the weight that's given by the marginal distribution of x. So this is the this is the expectation of the conditional mean of y given x. Now, we can manipulate this formula a little bit more by recalling what this conditional expectation is. By definition, this conditional expectation is a sample average of y with the weight that's given by the conditional distribution of y given x. Now we have a double sum over x and sum over y. And this conditional distribution, by definition, equals the joint distribution divided by the marginal distribution of the conditioning variable and multiplied by this this marginal distribution of the conditioning variable. Notice that this marginal distribution cancels out. So we are left with sum over both x and y, little y, joint distribution of y and x. And now if we exchange the order of the summation, which we can always do, and we get this. This y comes out because y doesn't depend on the x that the second summation is over. Now notice, what is this summation over x? That is the marginal distribution of y, because we summed the joint distribution over all possible values of x. So therefore, that is sum of y, sum over y, y times the marginal distribution of y. And what is this? That's exactly the definition of the unconditional mean, or the mean of y, the expectation of y. So what have we found? We have found that the expectation of the conditional mean of y equals the unconditional mean of y. And this equation is called the law of iterated expectations. The law of iterated expectation is exactly this. Expectation of the conditional mean of y given x equals the unconditional mean of y. Now let's consider an example that illustrates the law of iterated expectation. This is an example we have considered before. Here x, remember, it's gender variable, it's 0 if the random person is female, and it's 1 if the random person is male. And y is the vote in the general election. Y equals 0 means voting for Trump, and y equals 1 means voting for Biden. Now the joint distribution of x and y and the marginal distribution of x and y are given in this two-way table. We have calculated previously that the conditional mean of y, that's the expected vote for female, given x equals 0, is 0.8, and the expected vote for male is 0.4. We have calculated that. So that means the conditional mean of y takes two values. Conditional mean of y takes two values, 0.8 or 0.4. It takes the value 0.8 when x equals 0, and takes the value 0.4 when x equals 1. And what about the probability of these two values? And that's given by 0.5, given by the marginal distribution of x, which is here, 0.5 and 0.5. So it's easy to calculate that the expectation of this conditional mean of y given x is 0.8 times 0.5 plus 0.4 times 0.5, and that equals 0.6. This is calculating the iterated expectations. Now we can also calculate the unconditional expectation for y directly using the marginal distribution of y given here. And note that y takes two values, 0 and 1, each with probability 0.4 and 0.6. Therefore, the marginal, therefore, the expectation of y is 0.4 times 0 plus 0.6 times 1, which is 0.6. And clearly, these two are equal, demonstrating that the law of iterated expectation holds. Now, what about the conditional expectation of the conditional expectation? That's an interesting thought. We have figured out that the unconditional expectation of the conditional expectation is E of y. What about the conditional expectation of it given x? Well, to make the answer clear, we again denote that by a function g of x. Remember, this g function is defined to be expected value of y given x equals little x. So this is a function of x, and we can write down the joint distribution of x and g of x in this two-way table. So because x takes two values, 0 and 1, g of x takes two values, g of 0 and g of 1. Now, what's the probability that x equals 0 and g equals 0? Well, when x equals 0, g of x always equals g of 0. Therefore, that's the same as the probability that x equals 0. And there is no chance for x equal 1 and at the same time g of x equal g of 0. So that's 0. And similarly, there is no chance that x equals 0 and at the same time g of x equals 1. And therefore, the two-way table looks like this. So what's the conditional expectation of this g of x given x? Well, when the realization of x is 0, you are on this column where g of x can only have one value. That's g of 0. So given x equals 0, g of x can only be g of 0. And the conditional expectation is therefore g of 0. Similarly, g of x, expectation of g of x given x equals 1 is g of 1. So what are we getting? What we are getting is this conditional expectation of y given x equals conditional expectation of y given x, as if you are not taking the outer conditional expectation. Well, this is quite intuitive because e of y given x is a function of x. Now, if you are taking conditional expectation given x, because the value of x now is realized, is reviewed, then the value of e of y given x, this function of x, is also reviewed completely. So there is no longer any uncertainty once you are given the realization of x. Therefore, given x, conditional mean of y given x is a constant. And of course, the expectation of a constant is itself. So informally, we are getting this conditional conditional mean of y given x is constant, is non-random given x. So informally, this is what we are doing, and this will be quite useful in a lot of the revisions that we do later on. We can also calculate the variance of the conditional mean of y given x. The variance of this random variable, by definition, is equal to the expectation of its deviation from its mean. So EY given x minus its mean, which by the law of iterated expectation equals the expected value of y. Now there is a claim that we can decompose variance of y into two parts using the conditional variance of y and variance of the conditional mean. The variance of y can be written as the sum of these two parts. The first part is called the average within group variation. Average within group variance or variation. And the second part is called across group variation of y or cross group variation. Well, let me explain a little bit why these are called these names. If you look at the first term, you find that this is an average of something. It's an average of the conditional variance. Well, conditional variance of y given x is kind of the variance of y for people with the same value of x. For example, variance of y, given that x equals 0 in the previous example, is the variance of vote given female, or the variance of vote among female. Or variance of y given x equals 1 in that example is the variance of vote among male, among the male group. And if we average up all those within group variation, we get this average within group variation. So that's why this part is called within group variation. And the rest is called across group variation because that variance is a variation caused by the variation of the group variable. Now let's prove this claim starting with the definition of y, which is nothing but expectation of y minus ey squared. And the next step we do is to add and subtract terms. So we're gonna subtract e of y given x and then add the same term back. The purpose of doing that is to create a piece That is a component in the calculation of conditional variance of y given x, and also a piece that is a component in the calculation of the variance of the conditional mean. It's right here. So as you can guess, what we're going to do next is to expand the square term inside the square bracket. So we got a square term and the second square term and the cross product term. Y minus E of y given x, E of y given x minus EY. Now we can analyze the three terms one by one. For the first term, E of y minus EY given x squared, we move on to the next slide to calculate this term. What we do is to use the law of iterated expectation to write this outer expectation in terms of two iterated expectations. Here is just an application of the law of iterated expectation. Expectation of y minus EY given x squared given x, if you look at the term inside the outer square bracket, that is exactly the definition of the conditional variance of y given x. So therefore, that equals the average conditional variance. So that's the result. That's what the first term equals to. You can move it to the previous page. And that's the first term. And the second term we don't even have to move to the second page, to the next page to figure out, because this is exactly this formula. That's exactly the same. So therefore, the second term is variance of E of y given x. For the third term, for the cross product term, let's move to the second page. Notice that this is expectation of the product of y minus conditional mean of y and conditional mean of y minus the unconditional mean of y. So we move it here. In that, for that, we again apply the law of iterated expectation to turn the outer expectation into two iterated ones. Now we are going to work with the inner conditional expectation. We're going to work with this conditional expectation. Notice that this is a conditional expectation given x. Remember we talked about this. When x is given, any function of x is also given. Any function of x is constant with respect to this conditional mean. So are there functions of x? Oh, this is a function of x. E of y given x is a function of x. E of y is a constant function, also a function of x. Therefore, this difference is deterministic once you are given x. If it is deterministic, it can be put out, it can be factored out of this conditional expectation. And that's exactly what we do next. So we first pull out this function of x. Next, we're going to look at this part that we are left with after pulling out the function of x. This, notice, is a conditional expectation of the difference of two terms by the linearity of expectation. It can be written as this term can be written as e of y given x minus e of conditional mean of y given x and then given x. But conditional mean of the conditional mean is the conditional mean itself, right? Conditional mean given x of the conditional mean given x is the conditional mean itself. And the two terms are exactly the same, and the difference is 0. Therefore, this cross term is a big 0. Coming back to the previous page, this cross term is exactly 0. And we have concluded that the variance of y has this decomposition.